Welcome to the new video seminary. Here is Dr. Hoffman. Subscribe and give me likes. Let's start now.
Just as economists have worked out a theory of consumers, they also have developed a theory of producers. This theory explains what is behind the supply functions of the markets. The producers theory is concerned with the behavior of firms in hiring and combining productive inputs, factors of production, to supply commodities, outputs, at appropriate prices. Economists divide the factors of production into three categories: land, labor, capital. The first factor of production is land, but this includes whole physical space and any natural resources in it. Examples: water, timber, oil. Labor, the people able to transform resources into goods or services available for purchase. Capital is an important factor of production because it's what allows labor and land to be purchased. Steady streams of capital are often required in order to keep a business going. For example, money and equipment are considered capital. I marked in the red the two factors of production we will use in our theory today. Outputs or production function Q is the product company produces. In short run, that's a short period, there is this production function just the function of labor, because only labor is a variable factor. Capital is fixed and land is not considered. Total cost function equals to fixed cost plus variable cost. Company can't leave the industry in the short run and also can't enter other industry branches. Total product is the same like Q, production function. Average product, AP, is Q over L. Marginal product, MP, is the derivation of total product according to L. Then we distinguish cost functions. Short time total cost is fixed cost plus variable cost because both exist in short term. Average cost is average variable cost plus average fixed cost. Average variable cost is calculated like variable cost over Q, and average fixed cost is calculated as fixed cost over Q. In long run, there is also capital, which is variable. So the production function is the function of labor and capital. Total cost could be simplified because fixed cost doesn't exist. We have just total cost equal to variable cost. Company can leave the industry and also enter another one. Total product is the function of labor and capital, which are both variable. Average product of labor is the Q over L, and average product of capital is Q over K. Marginal product of labor is the derivation of total product according to L, and marginal product of capital is the derivative of total product according to K. Q function according to Cobb-Douglas equals to labor on alpha times capital on beta. We use the coefficients, we sum them up and then compare with 1. If it is less than 1, we speak about decreasing returns to scale. If the sum is 1, we speak about constant returns to scale. If the sum is larger than 1, we speak about increasing returns to scale. Long-run total cost function equals to variable cost, because fixed cost doesn't exist. Average cost is total cost over Q. Fixed cost R0. Marginal cost is the derivative of total cost according to Q. Production function is the relationship between production factors used in production. L here is labor, and maximum output Q here is the total product. From this situation we choose the increasing returns to variable input. Output increases more than proportionally to the increase in the variable input, so the total physical product curve rises steadily. We can calculate the marginal and average physical product for this graph given by L squared. Marginal product is 2L, as is the derivative, and average product is L, as it is L squared divided by L. Let's draw them to the graph, where the y-axis is marginal and average products, and the x-axis is labor. You see that both marginal physical product and average physical product increase, but the marginal product increases faster. So let's repeat that this situation in economic theory is called increasing returns to a variable factor in short run. Let's go to the second situation. We speak about diminishing returns to a variable factor in short run. Diminishing returns to the variable input are then experienced with the increase in output being less than proportional to the increase in the variable input. The total physical product curve flattens out, and both marginal physical product and average physical product, which we calculate now for the root of L, both decrease. So we can calculate them and draw them in the graph again. Average product also decreases. The axis L and AP, MP. You see that they both decrease. Marginal product decreases faster. So this was the diminishing returns to a variable factor in short run, second situation. So remember, these are the diminishing returns to a variable factor in short run. Let's go to the third situation. Constant returns to a variable factor in short run. L and U axis again, where output is increasing steadily as it is a line, in our example represented by the function q is 8L. Easy, we can calculate marginal and average products. Marginal product is the derivative. Since average product is just divided by L, the results are the same number. It's a constant, because by constant returns we experience the situation with the increase in output being exactly proportional to the increase in the variable input. Marginal physical product and average physical product are constant, here at the level 8. You see that their graph is represented by a constant. Let's speak about the progressive, degressive production function now. All points above the production function are unobtainable with current technology. All points below are technically feasible, and all points on the function show the maximum quantity of output obtainable at the specified level of usage of the input. From inflection point to TP max, the firm is experiencing positive but decreasing marginal returns to the variable input. As additional units of the input are employed, output increases but at a decreasing rate. To simplify the interpretation of a production function, it is common to divide its range into 3 stages. In stage 1, from the origin to the point T, the variable input is being used with increasing output per unit, the latter reaching a maximum at point T. Since the average physical product is at maximum, because the output per unit of the variable input is improving through stage 1, a price-taking firm will always operate beyond this stage. Point D is the point beyond which there are diminishing average returns. As shown by declining slope of the average physical product curve AP. Beyond point AP max. Point D is just tangent to the steepest ray from the origin, hence the average physical product is at maximum. In stage 2, output increases at a decreasing rate. It's the degressive part of our function. and the average and marginal physical product both decline. However, the average product of fixed inputs, not shown in the graph, is still rising because output is rising while fixed input usage is constant. In this stage, the employment of additional variable inputs increases the output per unit of fixed input, but decreases the output per unit of the variable input. The optimum input-output combination for the price-taking firm will be in stage 2, although a firm facing a downward-sloped demand curve might find it most profitable to operate in stage 2. Beyond point 2d, mathematical necessity requires that the marginal curve must be below the average curve, AB. In stage 3, too much variable input is being used relative to the available fixed inputs. Variable inputs are overutilized in the sense that their presence on the margin obstructs the production process rather than enhancing it. The output per unit of both the fixed and variable input declines throughout this stage. At the boundary between stage 2 and stage 3, the highest possible output is being obtained from the fixed input. Labor, L, capital K, and total production Q are drawn on the axis for the three-dimensional graph, where Q is TP, total production, which is a function of labor and capital. Here you can see the concrete three-dimensional graph with the points L2 and L1 for labor, and for them also the respective points K1 and K2 for capital. And here in the upper part, the points Q1 and Q2 for the total production. If you join the points, there is the same level of the total production. We call them isoquants. Iso comes from foreign language to English and means the same. So the same quantity. And now we know the production function in the long term with L for labor, K for capital, and also the function Q, total product, as set from isos and quantum from Greek language, the same level of the production, very similar to ordinalistic theory of utility. We can also mark the points L1 and K1 and say that here And here in K2L2, company has the same quantity or volume of production. And marginal rate of technical substitution shows us the relation of substitution of two factors without a change of total production. We can calculate it like that. Delta K over delta L. If you know marginal product of labor and the marginal product of capital, you can calculate marginal rate of technical substitution also in this fraction format. Very similar to Ordinal's theory of utility. Company doesn't want to know only the combinations of the products, of the factors of production, but also the level of total product and cost. So how to calculate total cost? It's the price of labor multiplied by the number of units of labor plus price of capital multiplied by the number of units of capital. This is the total cost function. You know that price of labor is wage, W, and the price of capital is rent. So interest, we can mark it R. Similarly to budget line, UC. And the total cost function is so-called isocost. So we can say it's a line TC. On the y-axis is capital, on the x-axis is labor, and the point coordinates L1, K1, and the other point coordinates L2, K2. On the isocost, there are the same cost in each point of this line. Its slope is given by the relation of prices of production factors, and we can mark it MERES, marginal rate of economic substitution. This marginal rate of economic substitution is the relation of price of labor and the price of capital. If we draw isoquant and isocost in the same graph, the first was isoquant, and here is the isocost. You can see that the isocost is touched by the isoquant in only one point, while isocost is a tangent of the isoquant of the curve. We can mark the point where they meet with the coordinates L with asterisks and K with asterisks. At this point the company gets to the maximum profit of the company, so-called E point, equilibrium point. And in this point, isocost and isoquant has the same slope. So in E, ES, marginal rate of economic substitution, equals to MRTS, marginal rate of technical substitution. We can write it also like that. The ratio of prices equals to the relation of marginal product of labor and marginal product of capital. Mark especially these two expressions for our next calculations. Let's draw the cost functions now, where on the axis X we have Q and on the y-axis TC, total cost. For the short run cost functions, there are fixed costs existing. In the case of progressive, degressive production function in short run, we have the cost functions also degressive, progressive. In the case of variable cost, and if we add them together with fixed cost, it moves us to the function STC, short run total costs. So this is the curve of short run total cost, which is a sum of fixed and variable costs. Let's add the average cost, which are diminishing with the growing level of production. So these are average fixed costs, average variable costs are growing. At first they are diminishing and then growing. And we can also draw short run average cost. They are the sum of average variable cost and average fixed cost. If you also add the marginal cost curve, it looks like that. So that we can write MC and AC, marginal and average costs, are on the y-axis. Let's do the first calculation for the production function Q equals to 10L plus 6L squared minus L on the third, where L is the number of employees in the company and Q is the number of products. What is the average product for the case where we have 3 employees? Is the first question. You know that the average product is calculated as the relation of Q and L. So we divide this formula through L, which is 10 plus 6L minus L squared. And for L3, we can calculate 10 plus 6 times 3 minus 3 squared. This is 18. This is 9. And we can say that 10 plus 18 minus 9 is 19. The B question, we should answer how much is marginal product for 2 employees in the case of the same production function. When we have 2 employees, L is 2, and we calculate marginal product. We know that marginal product is the derivative of the total product according to L. If I derive 10L, I get 10. 6L squared according to L derived is 12L, and minus L on 3 derived according to L is minus 3L squared. Now I can use the value L is 2 in our expression, and I get 10 plus 12 times 2 minus 3 times 2 squared, which is here 24, 12, 10 plus 24 minus 12 is 22. This is the marginal product. Let's go to the next question, C. We should find the Q, the amount of production from which average product AP decreases. So it means, according to the graph of AP, we are searching for the maximal AP. Let's see it in this graph. On the y-axis is average product, on the x-axis is the amount of labor. So for which Q is AP the maximum? And for which L? We are searching for these 2 coordinates. We are searching for the point AP maximum, which is the derivative of AP according to L. We know AP, and now the derivative of this expression is 6 minus 2L, and from here I can say that L is 3. If I supply this L in the expression 10 times L plus 6L squared minus L squared, I get 10 times 3 plus 6 times 3 squared minus 3 on 3, which is 57. Now I know both coordinates of the AP max point. So the company production Q from which AP decreases is in the point 57.3. Let's go to the last question, D, which asks us about the level of production Q when marginal product is at maximum. So we are searching for MP max. This is the function of marginal product. The maximum is there, where the derivative of the function of MP according to L equals to 0. We know MP function, it's 10 plus 12L minus 3L squared. Derivative according to L is 12 minus 6L. We are searching for L where this expression equals to 0, which is 2 for this L. We have the point MP max, coordinate L. The function of marginal product is maximal at this point. And we are also searching for the Q coordinate of this point. We are also measuring marginal product, so it's good to write it on the y-axis. Now let's use the L2 in this expression of total product to get the other coordinate Q. It means 10 times 2 plus 6 times 4 minus 2 on the 3 which is 20 plus 24 minus 8 which equals to 36. So we have the other coordinate Q, 36. This is the maximum marginal product. The marginal product has its maximum at the point. Marginal product is maximum by the point 36 level of production. And because the production function is only expressed by L factor, only one factor, it's a short run function. For the production function given by the expression Q equals to 8L plus 6L squared minus L to the 3, determine the AP function at first in the A point. We know the expression for calculation of AP, it's Q over L. So 8L divided by L is 8, 6L squared divided by L is 6L, and minus L squared on the 3 divided by L is L squared. In the B point, we will calculate the function of marginal product. We know that marginal product is a derivative of Q according to L. It means 8L derived according to L is 8, 6L squared derived according to L is 12L, and minus L on the 3 is derived according to L, 3L squared. Let's revise some rules for derivatives. From 8L I get to 8 according to this rule. 8 times L on the 1 minus 1, and 12L is the same like 6 times 2 times L on the 2 minus 1, and minus 3L squared is like 3 times L on the 3 minus 1. You see, the rule is easy. I always take the exponent before, then I multiply by the base, and from the original exponent I subtract 1. In the C point, we are asked to search for the amount of labor that company reached the maximum AP, and also calculate the amount of product Q. We know that AP maximum is the derivative of AP according to L, so this expression should be derived. And we search for the maximum point. It means where this expression is equal 0. From here you know that L equals 3. The other point, Q, by 3 employees, then the production function is 8 times 3 plus 6 times 3 squared minus 3 on the 3, which is 51. So this is the Q coordinate. And in the D point, we are asked to calculate the amount of labor where company reaches the maximum MP, marginal product, and also again what is the amount of product Q. For MP, the maximum, we are searching for derivative of MP according to L, where it is 0, so it's 12 minus 6L is 0. From here L is 2, and I will use this in the expression of Q function. It means 8 times 2 plus 6 times 2 squared minus 2 on the 3, which is 32. Again, it was only L, so short run production function. Only L is changing. You are now asked to select the type for the Q production functions written in this video frame. It could be diminishing returns to the variable input, or increasing returns to the variable input, or diminishing returns to scale, or increasing returns to scale. The first function is Q equals to 3L squared. The other Q is 8 times square root of K times square root of L. The third one, 4K L. The fourth one, Q is the square root of L. The fifth one, production function, is given in the form of 4K plus 2L. And the sixth production function is given as the square root of L times the cube root of K. And we also have the production function Q is 3 times the fraction, in the numerator L squared, in the denominator square root of K. Let's repeat the Cobb-Douglas production function as Q is L on the alpha times K on the beta. And if you sum the exponents and compare with 1, you know diminishing, constant, and growing or increasing returns to variable input or scale. These are the production functions in that form, but not the one with the x sign, because there is no multiplication but only subtraction or sum. For those where k is absent, we can write the k in the form as k on the 0. Now express the exponents alpha is 2 and beta is 0 in the first one. Here is k on the 1/2, so it means by L also 1/2. In the third example there is 1 by L and 1 by k for beta. In the fourth example, for L we have 1/2 for L and it's alpha, and 0 for k is beta. I skipped this one with x because it's not a correct form, and for L here is 1/2 in the case of alpha and 1/3 in the case of beta. And the very last production function, L was squared, so alpha is 2 and k in the denominator on 1/2 means on minus 1/2 in beta. Everybody knows that k square root from k is in denominator the same like k on the minus 1/2. From the Cobb-Laplace production function we know that we have to sum the exponents for the cases where there was no k, we added k on the 0, and now we have comparison. So the first case was increasing returns to variable input, and in the other one decreasing, diminishing returns to the variable input. In the case of those two functions we only have L, that's why we speak about returns to the variable input. In the other cases we also have the other production factor variable, so we speak about returns to scale. In this case it's exactly 1, so they are constant returns to scale. In this case they are increasing returns to scale. In this case it is 5/6, it's less than 1, and we speak about diminishing returns to scale. And in the last case we have 1.5, which is more than 1, and these returns to scale are increasing. And what about this form where we have sum instead of multiplication? We can use this expression instead to get multiplication. In the first case we have 1 and 0 in the case of alpha and beta, and in the other one 1 and 0 also, which is both 1/2 together 1, which is constant returns to scale. So by plus sign use this special form of calculation, alpha and beta. You can train it on very similar example, which I marked with X, like different from the other ones, because there will be again addition and not multiplication. 2L squared plus K. Again, we can reform as 2k on the 0 times L squared plus 2 times k on the 1 times L on the 0. Let's add 2 plus 0 divided by 2 plus 0 plus 1 divided by 2 suppose equals 1.5. That's more than 1, and we speak about increasing returns to scale. You can see that by the x-signed functions we couldn't just add alpha plus beta, but we divided them through 2 and compared with 1. Let's have the production function q equals 8l to the 2 plus lk plus 5k to the 3. We also know that we have 5 workers, L is 5, and 10 machines, K is 10. Let's search for marginal product of labor, MPL. You know that its formula is the derivative of Q according to L, which is for 8L squared, 8 times 2 times L to the 2 minus 1 plus L to the 1 minus 1 times K plus 0. From here, you know it's 16L plus 1 times K, which is plus K. This is the marginal product of labor, MPL, for this production function. We also add L5 and K10, which was known, which was given to us, and just supply them. We get marginal product of labor, 16 times 5 plus 10, it's 90. Let's calculate marginal product of capital MPK. In the B point, you know that marginal product of capital is the derivative of Q according to K. From 8L squared is 0. From LK it's L times Q to the 1 minus 1, and from 5K squared it's 5 times 2 times K to the 2 minus 1. It means, simplified, L plus 10K. Let's use L5K10, which was given, and we can express marginal product of capital, which is 5 plus 100, it means 105. For the cost function TC equals 2000 plus 40Q plus 4Q squared and 4Q10 pieces, specify total cost TC at first. It means total cost for 10 pieces is 2000 plus 40 times 10 plus 4 times 10 squared, together 2800. Average cost AC for 10 pieces is total cost divided through Q. It equals to 2,800 divided by 10, which is 280. Marginal cost MC. MC is the derivative of TC according to Q, which is 40 plus 8Q for 10 pieces, 40 plus 8 times 10, which is 120. Fixed cost FC, I can express FC from TC equals to FC plus VC. That's why total cost for 10 pieces is 2000 plus 40 times 10 plus 4 times 10 squared. From here, fixed cost is 2000. Variable cost VC at 10 pieces is 40 times 10 plus 4 times 10 squared. It means 800. Or alternatively, TC is FC plus VC. We already know that VC is TC minus FC. TC was 2800 and FC was 2000. If I subtract 2000 from 2800, I get 800 for variable cost at 10 pieces. For total cost TC equals 3000 if price of labor is 10 euros and price of capital is 20 euros and the function Q is 10 LK squared. Calculate in a point optimal combination of labor L and capital K. We know that optimum is the point where marginal product of labor divided by marginal product of capital equals to price of labor divided through price of capital. Marginal product of labor is the derivative of Q function according to L. It means 10K squared. Marginal product of capital is the derivative of Q function according to K. It means 20LK. If I use these both expressions in our fraction MPL over MPK, I get 10K squared over 20LK, which is 10/20ths. K over 2L is 1/2. K over L is 1. And from here, K equals L. Total cost equals to PL times L plus PK times K. It says that price of labor times units of labor plus price of capital times units of capital gives total cost. Here total cost was given 3000. You know the price of labor 10 euros times L plus price of capital 20 euros times K. For K, which equals to L, we can just write 3000 equals 10L plus 20L. It means 30 L's are 3000 and 1L is 100. And K from here is also 100 because L is equal to K. In B point, you should determine a total volume of production Q in the optimum point. Q for optimal 10 times LK squared is 10 times 100 times 100 squared, which means 10 million pieces. And in the last seed point, you should determine the type of revenues, if they are to scale or to a variable input, or if they are increasing or decreasing or constant. So for Q function 10 LK squared, we know that the alpha expression, alpha exponent is 1, and the beta exponent by k is 2. If we sum them together, 1 plus 2 is 3, which is more than 1, and we speak about increasing returns to scale. To scale because we have L and K variable factors, and we are in the long term.
At the end, there is just to say subscribe and give me likes. See you soon!